Very good then. Today, we're going to start by looking at section 1.5. And here we're going to talk again. We've been talking about like attributes of functions, like ways that, adjectives we can use to describe certain ways the functions look or they behave or whatever. And we're still kind of in that process. We're going to be living in this world for a couple more days. So we talked about, how to tell if something's a function or not. We've talked about domains and ranges. We've talked about intervals of increasing and decreasing and constant. And then we talked about extrema, the local maxes and mins or global maxes and mins. Today we're going to be talking about symmetry. So there's three types of symmetry. So there's symmetry with respect to the x-axis. There's symmetry with respect to the y-axis. We call functions with this particular symmetry even functions. And then the third is 180-degree point symmetry with respect to the origin. And we call these functions with that particular symmetry odd functions. So those are the three types. Let's look at some examples here. We'll write an example as an equation. We'll write an example. We'll write that same example then as a graph and as an XY table, so you can kind of get a feel for like, what am I looking at to notice something is each one of those type of symmetries. So let's say, so here are the symmetry with respect to the x-axis. So if you have the equation x equals y squared, or what would that look like if we rearranged it so it was a y equal equation? Right, we've just been doing this recently, right? If I wanted to rearrange x equals y squared so that I could type it into my calculator as a y equals equation, what would it look like? Square root of x? Almost. We forgot something though. Close. Plus or minus. There you go. Remember, when you take the square root of both sides of an equation, it generates a plus or minus. I'm going to remind you of that the entire semester, and still some of us are going to forget to do it. Try to really be careful though. That's something that's really easy to mess up on like a standardized ACT test. Most of us that are juniors will probably be doing that at some point this year. Easy mistake to make, or if you've already taken one maybe recently. Just like a good thing to be aware of. I guarantee you there'll be multiple places on the ACT where one of the answer available is if you didn't do the plus or minus, and then other answer available if you do have the plus or minus, and it's easy to miss. Okay, so that's an example of an equation where we have this symmetry about the x-axis. If I were to graph this, the graph would kind of look like this. Come on back. Yoo-hoo. mistake maybe. Is it coming back? You're coming back? Has this not been on at all?
No, it hasn't.
It has, and it clicked off, right? Very strange. Apparently that just like randomly powered down. It wasn't even, I don't know. I wonder if you hacking into the Wi-Fi here and messing with my projector. Who here is the global threat level hacker? Okay. Anyways, this is what the graph would look like if we are symmetric about the x-axis. What do you notice about this graph?
Vertical line test.
It's not a function because it fails the vertical line test. Very good. And if you look, if I took, say, this point here, let's say that's A, and this is then like the y coordinate, or the point A comma f of A. Down here, this point would be the point A comma negative f of A, right? Where the y coordinate is the same, it just has a negative sign attached to it. Is everybody good with that? So what are we saying here? If I look at like a set of points, so 9 could have the y value -3 or +3. 4 could have the y value -2 or +2. 1 could have the y value 1 or -1. And then 0 is just going to be 0, right? Because 0 is neither positive nor negative. So the plus or minus doesn't affect 0. But that's kind of what we're looking at here. Everybody okay here? So my observation is that f of x would equal negative f of x. Yes, sir.
Do we have another homework with this chapter?
Possibly. Possibly not.
So it's you won't tell us, you'll just surprise us.
Sometimes I'll give you I'd like an idea that there's one coming, but they're more or less unannounced. You're convinced, huh? Okay. Let's look at what it would mean for the symmetry with respect to the y-axis. So let's look at an equation there. Let's just say we have y equals x squared. So the graph of y equals x squared look like this. Try to draw that a little bit better. This is maybe smidge better. Everybody's okay here? So what we should notice here is if I have the point or the x value a, and that's the point f of a, over here we should have negative a. I should put that over by the point so it doesn't look like I'm labeling the x-axis. That's just making life unclear. me draw it this way. So if I have the point a comma f of a, I should also have the point then negative a comma f of a. If I look at this, if I think about this as like a mirror, whoa, what just happened? The point should be like a reflection of one another across that mirror, right? Like if I take this point and fold it across that squiggly line, I should land still on the function. I should be able to do that for every point. Same idea for symmetric about the x-axis. If I take this point and I fold it across the x-axis, I should land again on the function. Does that kind of see that? Okay. So what would the xy table here look like? We should notice that like the y-coordinate for -3 and +3 should be the same. The y-coordinate for -2 and +2 should be the same. The y-coordinate for -1 and +1 should be the same. In general, you want to say that negative or f of negative x should equal f of x. Right? If I do f of -2 and f of +2, I should get the same value. Everybody feels okay? Okay. All right, so let's look at the last one here. So let's look at this 180-degree point symmetry. So an example of the equation could be something like y equals x cubed. So my graph would look something like this. So here, if I have the point a comma f of a, I should also have the point -a comma negative f of a. So the idea here is that we kind of have a reflection across the y-axis and then a reflection across the x-axis. If we do both those two consecutively, we land back on our function again. So this 180-degree point symmetry is kind of like both an x-axis symmetry and then a y-axis symmetry. And it actually doesn't matter the order in which you do it. You could do the x first and then the y, and you still end up with the same thing. So why do we call it 180-degree point symmetry, Mr. Kulik? Okay, well, this is the idea. So suppose that we build a little anchor here at the origin and attach a rope to our point, and we swing that point like 180 degrees, like a half a circle. If we do that, we're going to end up back on the function, right? That's why we call it 180-degree point symmetry, but it's the same thing as that symmetry across the x and then symmetry across the y. But that's the idea. That's where the name comes from anyways. So far, so good. So really all we've done is we've looked at some pictures, right? Oh, like we should give a table for this, right? I got carried away here. Okay. Oops. What am I doing here, Mr. Kulak? I don't know. Counting is hard sometimes, guys. So again, here we notice that -3 and +3, y-coordinates are opposites. -2 and +2, again, the y-coordinate are opposites. And -1 and +1, the y-coordinates are opposites. The observation I'd want to make here is that negative f of x is equal to negative, or f of negative x is equal to negative f of x. Okay, so far so good? Let's just do that easier. So I'm going to add in a little addition here to our instructions. We're going to determine and then we're going to prove whether the following functions are odd, even, or neither. So first thing that I would do is I would look at the picture to try to figure out which one I'm going for, right? So I will just start by typing this into my calculator. Get rid of this stuff. Okay, so here's the graph of x to the fourth plus 1. What does this look like? Odd, even, or neither? Okay, so remember we said at the beginning odd was these, the 180-degree point symmetry, even is the respect to the y-axis. So that one does look even, right? Okay, so now we're going to do the proof. Here's the cool part about the proof. It's really prescriptive. So the things that we're going to need to do our proof are going to be these observations. Okay? Specifically, since we're asking about odd or even, really just these two observations. Everybody's okay so far? You know what's the awesome thing about these two observations is that they start the same way. So regardless of whether this thing is going to be odd or if it's going to be even or going to be neither, I'm always going to start by just doing f of negative x. So far, so good? Okay, so that's where we're going to start. Now, what should I be doing if I'm plugging in, or if I write f of negative x? Okay, what if I'd written f of negative 2? What would I do? What would that tell me to do if I just wrote f of negative 2? Right, as I would replace the negative, or the x with a negative 2. Everybody's cool with that? So if I want to do f of negative x, I'm just going to replace the x with a negative x. Oh, okay, Mr. Kulik. NBD. Everybody's okay with that? No big deal?
Yeah.
No.
She thinks she's so cool.
Okay.
No.
So, I've done the hard part now. All I'm going to do is a little bit of simplification. What's negative x to the fourth power equal to? How do I simplify that? What does it mean to be to the fourth power?
Times negative 2 4 times.
Okay, well, we mean negative x 4 times, but yes, that's okay. Right? That's just what negative x to the fourth power means. So when I multiply 4 negatives together, what do I get?
Positive.
A positive. And if I multiply 4 x's together, I get x to the fourth. So I have positive x to the fourth. Ava, what's up? I was just doing that's just like an aside. Because when I asked, what do I do when I have f of negative x, nobody was answering. So I'm like, okay, what if I just had f of negative 2? What would I do? Oh, you plug negative 2 in. No, this was just to get you guys to see what I was trying to get to. That had nothing to do with the problem. It was just like an aside. You know, like sometimes I ask a question and nobody knows the answer, so I'm like, okay, let me ask an easier version of the same question so you can see what to do to get the answer. That's all I was trying to do there. Is that okay? Okay. All right. And what is x to the fourth plus 1? That's f of x, right? Everybody agree?
Yes, sir.
So look at what we've done. We've shown that f of negative x is equal to f of x, right? And that tells me that f of x is even. That's what I need to show in order to complete my proof. Remember, if we went back up and looked at our observation, for even, that's what we needed, right? That f of negative x is equal to f of x. And what did we show down here? F of negative x is equal to f of x. So we're done! Let's try the next one. So let's go to the calculator and we'll type in our g of x now. Everybody okay so far? Okay, I'm going to hit graph and look at our picture. Which one does this look like? This to me looks odd, right? Because if I look at like this quadrant, looks the same as this quadrant, right? It just kind of turned around. That's odd. Everybody can see that?
Yes, sir.
If we go back and look at our picture of the odd one, right? That's kind of what we're seeing.
It's a little odd.
It's a little odd.
It's kind of like,
I know.
Now let's look at what we need to show to be odd again. We need this, right? That f of negative x is equal to negative f of x. So we're going to start the same way. So what are we going to do if we have f of negative x? What do we have to write? And go back to the original equation and replace all the x's with negative x's, right? So I still have 2, and then in place of x, I'm going to have negative x, and then I still have the third power. Then I have plus 3, and instead of x, I'm going to write negative x. So far, so good? Okay. All right, how do I simplify 2 to the negative, or 2 times negative x to the third plus 3 times negative x? So if I multiply 3 negatives, what do I get? Negative. So that part's just going to be negative 2x cubed. When I multiply a negative and a positive, I get a negative. So that's just going to be minus 3x. So far, so good? Okay. Well, since we're odd, we're trying to get to negative f of x, right? Remember, that's the observation. So I'm going to now factor out a negative sign. Everybody's okay there?
yeah, can you scroll a lot to us? I can write the
How about that? I didn't scroll, but I just,
didn't look or made it scroll.
yeah, I zoomed a little. And if I'm going too fast, or if you have a question or you're not sure, you just like, I need to talk about this for a minute, or I just need a second to think, you know, say something. We can pause. I can re-explain. We can have a conversation about what's confusing you. All that's okay, right? We want to do a good job. We want to get it right the first time. If you're not sure,
Do we just compare, like, we just plug it in and compare the graph to the...
well, that's to figure out the answer, but to do the proof part, we need to do what we're doing now algebraically. So now let's look at what we have. What is 2x cubed plus 3x? That's just g of x, right? If I go back and I look at the original problem, right, 2x cubed plus 3x, which is what we have right down here. That was supposed to be a g. So look at what we have. g of negative x is equal to negative g of x. That's what we wanted to show. Yes. Sure. Okay. Questions so far?
This is all the same problem.
Well, these are three different parts to the same question, right? I have a part A, B, and C.
Oh, okay. No, I was just confused.
Let's do part C then. So I have 4x squared minus 3x plus 9. So let's go ahead and hit graph. I see a little bit of up here, but I can't really tell what's going on. So I'm going to adjust my window here a little bit. All right, odd, even, or neither? What does it look like to you guys? Looks neither to me also. Why isn't it even though? Looks like I have a little bit more on the right side than I do on the left side. Everybody agree? If it was truly even, it would be split, right? Dead center down the middle. Everybody agree? Okay. So this one looks like neither. Well, to do a neither, how do I do that, Mr. Gulick? Well, we start the same way. So we start by doing h of negative x. What does h of negative x mean? Plug negative x in for x, right? So instead of 4x squared, we have 4 times negative x squared. Instead of negative 3x, we have negative 3 times negative x. And plus 9, well, there's no x's, so it just stays plus 9. Is everybody okay with how I plugged that in? Okay. So what is 4 times negative x squared? How do I simplify that? What's negative x squared simplify to? X squared. So that just turns into 4 times x squared. Good. Thanks, Ellie. And then what's negative 3 times negative x?
3x.
Positive 3x. Great. And then plus 9 just stays plus 9. Now notice that what we have here is not our h of x, right? Everybody see that? So we know it's not even. Everybody okay with that? What I'll do next is I'm going to factor out a negative sign. So since everything was positive, factoring out a negative is going to swap everything to be negative. And that part is not equal to negative h of x. So we know we're not odd either. So since h of x, h of negative x is not equal to h of x, and h of negative x is not equal to negative h of x, we can say h of x is neither even or odd. Yes, Nora. Certainly. Okay. So far, so good? Okay. So at this point, you guys should now be able to do like 19 through 22. Yes, Paul. Yes. What time is this thing at? I'm trying to decide what it is. 40. Okay. All right. So next thing I want to do then is we're going to talk about asymptotes. So we say that an asymptote of a graph is a line that the graph approaches but never touches. These asymptotes can either be horizontal or vertical. When we say approaches in mathematics, what we mean is that the graph will get closer and closer and closer to that given line, but won't actually ever get there. Now, notice that I have a star here next to the word horizontal. And the reason that is because as far as we're concerned, we're still going to count things as horizontal asymptotes, even if we might have some touching in the middle of the function, but the ends we should never get a touch at. So we'll draw some pictures here in a minute and kind of show you what I mean by that. So we're going to refer to some things as horizontal asymptotes, even though the graph might touch them, so as long as at the ends the graph is still having that asymptotic behavior of getting closer and closer and closer, but never actually reaching it. So let's look at an example here. Let's say we have this function here, so y equals x squared plus 3x minus 3 over x squared plus 2x minus 3. Actually, I'm going to graph this on a different piece of software so that it's a little easier to embed the image, because I want to draw on this picture. So I'm going to graph it in this program. This is called Graphmatica. It's a free download if you're interested. It's a little Google search. You might need somebody from IT to okay the download though, because I don't think you guys have willy-nilly free downloads and installs of programs. Do you guys?
Yeah, we don't have any rights.
Yeah, so you'd have to probably get somebody from IT to okay it for you, but they should. Just tell them it's a piece of educational software, whatever it's the name of it. They should probably heard it. So this is what our picture ends up looking like. I'm going to just grab that image and drop it into the OneNote so we can try to draw some pictures. So when I look at this picture, I think I see 3 asymptotes. I see 2 vertical ones and 1 horizontal. So it looks like here I see a vertical one at -3. So if I kind of draw on that vertical line, it appears that the graph gets closer and closer and closer to that vertical line, but never actually reaches it. I think I see another vertical asymptote here at +1, because I kind of see the same thing happening. Yes, sir. Of course. Everybody see those 2? And then I see a horizontal at, well, it looks like y equals 1, right? So if I draw a horizontal line here, again, I notice that I'm crossing here in the middle. That's okay, because I get that asymptotic approaching behavior at the ends. We're still going to call that one a horizontal asymptote. So the vertical asymptotes we always write as x equals, right? That's the way we graph or write the equation for a vertical line as x equals. So I'd write x equals 1 because if I look at that vertical line, every point on that line has the same x coordinate. It's 1. Everybody see that? So the horizontal line, we write y equals, because if I look at all the points along that horizontal line, they all have the same y coordinate. It's 1. Does everybody feel okay with how I visually identify these asymptotes? And then how I wrote the equations for them? The verticals start x equals, the horizontals start y equals. Now, one of the things that I am going to ask you to do when identifying these asymptotes is I'm going to ask you to create a table of values to justify what we're seeing. So to do this, I am going to use my calculator. So let me go type this equation in real quick. Now, because there's a fraction bar, I'm going to do this shortcut to put the horizontal fraction bar in my calculator so I can type it in exactly like it looks on my sheet of paper. To do that, I press alpha and then y equals, and then pick option 1. And then I can just type this in exactly like it looks on my sheet of paper, which is really nice to not have to muck around with like a whole heap of parentheses, because that's just like a good way to ruin a day, good day, is to try to make sure I got all my parentheses right. Okay. And then I'm just going to go ahead and look at the picture of this right quick to make sure that I didn't type this in wrong, which I kind of now think I did. Oh, sure did. Look, I missed the plus sign in that denominator. Good thing I looked, huh? Did you know if you press second and then the delete key, see in blue it says INS, that's short for insert. So I can insert a symbol in between those without over-typing things. It's a nice little thing to know. Now if I graph, now this looks just like I did before, right?
Yeah.
Now I'm pretty convinced I got this in right. Okay. So what we want to do, we're going to look at each of these separately. So for a table for the asymptote x equals 1, what I want to do is I want to look at x values as they're getting closer and closer to 1 from values that are bigger than 1. So I'm going to look at those values. And then I'm going to do the same thing for values that are less than 1. They're getting closer and closer to 1. So those are the values of x that I'm going to evaluate. Everybody's okay with what I'm doing? Okay. So the easiest way to plug those in to this equation is not to do that by hand. I can ask the calculator to just plug them in for me. You just have to know how to ask it. So what I want to do is if I treat this as like, if I think about this as f of x instead of y equals, to do this would be like f of 1.1, right? Everybody agree with that? Guess what? The calculator will recognize this. So what was the name of the function we named this one? y1. So we're going to do the same thing. We're going to write y1 of 1.1. So the only thing we need to really know is where do I get the y1 symbol on my calculator? So no, actually. So we're going to go back to our main screen, and we're going to press the vars button here that's right underneath the down arrow. Now we're looking for y1. That's a y variable. Vars is short for variables. So I'm going to move my tab over so that I'm on the y vars tab. In this class, we're going to be in function mode, I think all year. So I'm going to pick function option. And look, there's the y1 right there. So I'm going to press enter. And then I'll write a parenthesis to do y1 of 1.1. So I'm going to write that number down. Now, instead of navigating back through all those menus to get that y1 symbol again, what I'm going to do is I'm going to press second and the enter button. That's going to recall the last thing that I typed into my calculator. And I'm just going to go back and edit the 1.1 to be 1.01. And then second and enter. and I'll make that 1.001. And I'm just going to keep going, second and enter. And I'm going to change this to 0.9. And then 0.99. And then 0.999. And what do I notice here as I'm getting closer and closer to 1 from the right, from the values that are bigger than 1? What does it appear that the y is heading towards? It's like it's going to positive infinity, right? Those numbers just keep getting bigger and bigger and bigger, right? By almost a magnitude of 10 at least, right? What about these ones? What does it appear that we're going to there? Negative infinity. So these are what tell me that I'm getting a vertical asymptote when it appears the y coordinates are growing very quickly without bound. Okay, let's do this again now for our other asymptote, which was at x equals, was it 3? Negative 3. Ooh, good thing I checked. So again, I'm going to start the same way. I'm going to start from something a little less than negative 3, and then get closer and closer to negative 3. And then start with something a little bit bigger than negative 3, and get closer and closer to negative 3. Now it's still the same function in my y equals, right? So I can just keep doing second and enter and adjust my inputs. So here I'm just going to adjust this to negative 3.1, and then just kind of keep going. And 3.01, and then 3.001. Now I'll pause and write this stuff down. And again, what am I noticing here? That y is heading towards negative infinity. That's great. Let's go back and do the other half now. So again, second and enter, and I'm just going to, again, update what's going in. Isn't this way better than trying to type all this stuff into your calculator over and over again?
Yeah.
Yeah, buddy. Okay, 844, 7594, and then 75094. And again, because these are heading towards infinities, that's my justification that I have a vertical asymptote. Is everybody okay so far? We have one more to do, right? We have the horizontal asymptote still to do. So that one was at y equals 1, right? Now this is going to be a little bit different how we set this up. Right? If we go back and we look at our picture, the vertical asymptote happened right as we're getting closer and closer to -3, and then again as we got closer and closer to +1, right? Is that correct? The horizontal asymptote, what x value are we getting closer and closer to? It's positive infinity, isn't it? And the other end is -infinity, right? So what x values should I pick? Well, I'm going to do like 10, 100, and then 1,000 for positive infinity, and then -10, -100, and -1,000 for negative infinity. And what y value should we be expecting to see this getting closer and closer to? Should be 1, right? Because that's what the y is, right? The horizontal asymptote is y equals 1. Here we're finding the y's, right? So we should be getting closer and closer to 1. For the vertical asymptotes, we're getting closer and closer to x, and the y's going to infinity. For the horizontal asymptotes, we're getting closer and closer to infinity, but the y is going to a finite value. Okay. Go back here, and again, still the same thing we're plugging in, right? So I'll just second and enter and just update this. So 10. Uh-oh, Mr. Kulik, what do I do with this? I can get a kooky fraction out of this. Well, if you don't want a fraction, if you'd rather have a decimal, which I would, I'm going to recall the same thing, and after it, I'm going to press math, and I'm going to go ahead and pick this decimal option, and that just tells the calculator, no, man, give me the decimal, not the fraction. So we'll do that, and then I'll do second insert, make that 100, and second delete, so insert another 0, make that 1,000. What do you notice that y value is getting closer and closer and closer to? 1, right? So now we'll go and do the other way. Second, enter. Go back and make that -10. And then -100. And then -1,000. Bless you. So here we get y's heading towards 1. Since those are both heading towards the same finite value, that's telling me we're getting the horizontal asymptote. Now this is time consuming, right? But is it difficult? No, man, not really, right? Pretty easy. This is where we're going to stop here for today. For the homework, you guys should be able to do now 23 and 24 as well. I want to point out to you as well, I made a Delta Math assignment for us. Oh, yay, Delta Math. It's just called Chapter 1, Delta Math number 1. So there are, let's see, 1, 2, 3, 4, 5, 6 different types of problems. You have to do 4 correct. just so you know, if you get much past like the fourth set, we haven't talked about inverses yet, but we have talked about this stuff in the beginning. So I just wanted to kind of give this to you. We'll come back and we'll work on some more. You can work on it as the chapter goes on. I'll remind you again once we get through inverses that like, hey, you could now be able to finish the delta math. But I wanted to like just kind of get this started here a little bit. Everybody okay? So again, the first 2 or 3 sections should be no problem. Stuff we did already last week. As you get further on, it'll be stuff we're getting to here in the next coming chapters. Okay? Any questions for me? Okay. I'm good. You guys can take the last 10 or 15 minutes here to kind of get started on the new stuff, maybe fire up your delta math and start on that, wherever you want to start. I think the due date for this I have set for September 3rd, so that's this Sunday. If I have to adjust that, we'll adjust that. It's not set in stone now, but you know, I would start on the parts that you're already able to do. Shouldn't be too time consuming, presumingly that you're getting things right. If you're getting things wrong, it's a nightmare, and we've all been there, right? You guys all did delta math a little bit last year.
Yeah.
There's no penalty for wrong answers, okay? You just have to get 4 correct to move on to the next section. Doesn't matter how many you get wrong. They don't have to be 4 in a row, just 4 total right. It's a by completion assignment, not graded right or wrong. I mean, delta math's grading stuff right or wrong, but I'm not looking at that part. Everybody cool? Okay. Try not to take like 100 tries to do a problem, but like if it takes you 100 tries, you don't have to fret about it. You know what I mean? Like don't just go guessing at stuff. But like try to do it, you know. But if you make a mistake, don't be like get bent out of shape about it or nothing. And if you keep getting stuff wrong and you are getting bent out of shape and you just don't know what's going on, come see me. You know, we can talk through it. Sometimes the directions are kind of obtuse as to what they want you to do. I tried to pick things where that wasn't really the case, where it was pretty easy to like answer the question. You'd have to like draw a graph and pick a scale and do like a bunch of weird things to like answer the question. Although occasionally we'll pick problems like that, but I think this first time through I tried to pick everything that was pretty self-evident.